Hello, students. Today, I would like to share with you an introduction to the specific heat lab. So the lab is titled Determination of Specific Heat. Specific heat of a substance or of a substance. Could be a substance or a material All right. First of all, I would like to state the definition for specific heat. What is a specific heat? When we talk about specific heat of a substance, what are we trying to say? So specific heat is defined as follows. Specific heat is defined as the amount of heat energy required to raise trying to be fast. Required to raise 1 gram of a substance, 1 gram of a substance by 1 degree Celsius. So that's the specific heat. Some people will call this one specific heat capacity, but I'm going to call it specific heat as the amount of heat energy required to raise 1 gram of a substance by 1 degree Celsius. Let me give examples. For copper, which is a metal, we need 0.385 joules of heat energy in order to raise 1 gram of copper by 1 degree Celsius. So this is how we write the specific heat of copper. We write it like that. Now for Pyrex glass, let's look at Pyrex glass. For Pyrex glass, we need 0.700 joules of energy to raise 1 gram of Pyrex by 1 degree Celsius. And for aluminum, just give you a few more substances. For aluminum, we need 0.890 joules of energy to raise 1 gram of aluminum by 1 degree Celsius. And that's how we write the specific heat. So these numbers you see here are what we call specific heat of these substances. These are specific heats. All right, specific heat of these substances. They are known values. And in this lab, we are going to learn how to determine these values. That's our purpose. Our purpose is to learn how to experimentally determine the specific heat as they are right now here. I forgot, we have to add the water. Water is very common substance, and we need 4.184 joules of energy to raise 1 gram of water by 1 degree Celsius. Okay, that's for water. There's a point here. I don't know if you can see it. Let me do this. Oh, sorry. So 4 point. Okay. Now let's look at the experimental setup. So this one, you need to have an insulated container. I'm going to explain the reason very soon why the container must be insulated. So this is all insulated. Well, I can tell you, you can guess an insulator actually will prevent heat entry or heat loss. So this prevents heat entry or heat loss. So this is an insulator. You need to have an insulator, and then you need to have a way to measure the temperature of the inside. That should be a thermometer. This is a thermometer. Okay, that's a thermometer. The reason is we should be able to measure the temperature of the contents thermometer here. And then what you do, you heat up a given material. So heat up the specimen or the substance, heat up the substance, all right, say to what? Maybe 90 degrees Celsius. It has to be high, hot enough. Of course, you shouldn't melt it, at least give it some heat energy. Then you need to actually mix the substance with water. So you mix the heated, you're going to the heated what? Material with water. Of course, you have to make sure the water was initially at room temperature. So the water has to be initially at room temperature. Right? For example, 24 degrees Celsius. So this mixing has to be done very fast, and it has to be done in the container here, which we call calorimeter. Some people call this one insulator, or the whole thing here is called a calorimeter. Calorimeter. Okay. So you're going to make sure that you drop all the metal pellets or the crushed metal or crushed the glass, whatever substance you have, drop it into the calorimeter, drop it into the container, and it has to be done fast. And you have to make sure that before you drop it, the water is already there. The water that I talked about, the water at room temperature has to be inside already here. So this is the water, or this is the water. And the water is actually mixed together with the substance or the metal pellets. Is a substance or metal pellets. Okay. All right, so you can guess that the water was initially at room temperature, 24 degrees Celsius, and you just dropped in metal, which was heated to 90 degrees Celsius. What will happen is that some of the energy will transfer into the water. So in other words, the water will gain some heat energy. Eventually, the mixture will reach equilibrium temperature, and that equilibrium temperature is very, very important for you to find the specific heat of the metal or of a substance. All right, so let me come again. So first of all, you're going to put water. That should be water at room temperature in the calorimeter, some water in the calorimeter in this container. And that water must be at room temperature, about 24 degrees Celsius. And you drop the heated metal. So drop the heated metal about 90 degrees Celsius hot. Drop that into the calorimeter and cover the calorimeter quickly and observe the temperature changes on the thermometer until the temperature stops moving. Until if you see that the liquid in the thermometer or the temperature is stabilized, then you stop there. That will be your equilibrium temperature, and we will need that to find our specific heat capacity of the metal. Now let's come back to the physics. Now remember the conservation of energy. It says what? It says that energy cannot be destroyed or created. Energy can only transform from one form to another. The same thing here, we are going to see that the heat lost by the metal, the heat lost by metal or material, let's just say material, because we may have different substances, glass, metal. So heat lost by the metal must be equal to heat gained by the water. Heat gained by water. This should be the case because that's the conservation of energy. Whatever we lose, that's whatever we gain. Remember, we have an insulator. So we cannot worry about heat loss to the environment, or we cannot worry about heat gained from the environment. So we are sure that we have an isolated system. Now, in terms of symbols, this will be Q of the material, and this will be Q of the water. And I can break this one further because I have to understand what is heat. By the way, I think I skipped one stage. I didn't connect the specific heat. Remember, we mentioned about this definition here. That's the definition for specific heat. I did not connect the heat energy, the mass, and the specific heat value. So let me do that here, right here. So there is a connection between if I want to find the amount of heat energy lost by the metal, I have to multiply the specific heat of the metal times the mass of the metal or material, then times the change in temperature, This will give me the specific heat of the metal. And this one too here be equal to mass of the metal times mass of the, sorry, I should start by specific heat. Specific heat of the water times mass of the water times the change in temperature of the associated with the water. Change in temperature associated with the water, we just write it like that. All right, so this formula works because, I mean, before we break this one down, I want to show you how it works. The specific heat is in joules, and then slash grams degrees Celsius. I'm just looking at the units. And then the mass will be in grams if you are to be consistent. And the temperature, change in temperature will be in degrees Celsius. So if you cancel a gram, let me use a different marker. A gram and a gram goes, degrees Celsius goes out. You remain with a joule. So that indeed tells you it's the amount of heat energy lost, right? So this actually works. This formula is the formula for the heat lost or heat gained. Okay, so let me go back. Okay, so let me break down this formula again. So this will look like specific heat of the metal, specific heat of the metal times mass of the metal. Now times, let's look at the change in temperature associated with the metal. The metal starts from a higher temperature, let's say 90 degrees Celsius, and then goes to equilibrium temperature. So if I wanted a change in temperature to be positive, I must subtract initial temperature of the water, that's initial temperature of the metal. T naught M is initial temperature of the metal, just before you mix it with the water, minus temperature of the what? Or temperature of the final temperature, that's equilibrium temperature of the mixture. And this one is a specific heat of the water, CW, times mass of the water. So mass of the water will be mass of the water, MW. Now I want the change in temperature associated with the water. Remember, the water starts from equilibrium temperature of T naught W to T final. So the higher number will be T final. The smaller number will be in room temperature number, T naught of water, like this, right? All these quantities can be measured actually, apart from this, which you have to know. The specific heat of water has to be known. So I'm going to isolate Cm on one side of the equation. So Cm will be everything here divided by everything here. So C specific heat of water times mass of the water times final temperature, equilibrium temperature, minus initial temperature of the water, which is about 24 degrees Celsius, divided by mass of the material, could be a metal or a glass, times change in temperature associated with the metal, will be initial temperature of the metal before you mix it with the water, minus final temperature of the mixture. That's the change in temperature associated with the metal. Again, this can be measured. Let me use a different marker. Okay, this can be measured, mass of the water. You can measure it before you do the experiment. The final temperature can be measured using a thermometer. You remember this? This is used to measure the final temperature of the mixture. Remember that? Then you have temperature of the water initially, which you have to measure before you mix it with the metal. Mass of the metal can be measured, or mass of the material. You can measure that in the experiment or before or after. Temperature, initial temperature of the metal. Yes, you have to know it. You have to heat the metal separately. Before you drop it into the calorimeter, make sure you know how hot the metal is. And final temperature is the equilibrium temperature. The only thing that you have to know from the previous understanding of previous learning or from the internet or a table of specific heat capacities is the specific heat capacity of water, which is 4.184 joules per gram degree Celsius. So this number has to be known. Then you can find your specific heat of the metal or material. This is the formula you are going to use. By the way, in this lab, I want you to determine the specific heat of 3 substances. You're going to determine specific heat of copper. I'm using Cu in the lab manual, Cu for copper. And let me see. We have also aluminum. So you're going to determine specific heat of aluminum. Usually it's Al. So I would say specific heat of copper will be symbol will be like this. And for aluminum, I just put C, I think Al, if I'm not mistaken. Al. And then there's Pyrex glass. I would like you also to find the specific heat. And this one, I don't know how I represented it. I think it's C glass. I just put this in the lab manual, C glass. So you are finding the specific heat of copper, specific heat of aluminum, and specific heat of glass. Remember, I already gave you the results. I already gave you the known values. So do not assume that we have them already. Assume that we do not know. Use the data from the video. I'm going to share the link to the video in the maybe somewhere before I upload this video on YouTube. I will upload the link to the data collection. Right? So the link will show you how data was obtained, and you just have to pick out numbers, relevant numbers, so that you should be able to solve for your specific heat here. So again, we are going to find a specific heat of 3 substances and compare them with the known values. That means I would like you to calculate percentage error to see how close your results are to the expected results. So you're going to have experimental value. I'll just put experimental value minus known value. Then you divide by the known value times 100. Of course, you put a percent here. So this is very important. It will tell you whether your results are close to the expert results or are close to the known values. And that can give you a chance to describe or discuss the sources of error. So it is very important to think about why your results or why your experimental values might not be exactly equal to the known values. Think about the measurement, think about the assumptions we made in the lab, think about the equipment we used, think about the principle of energy conservation if we have actually, ideally, if we have practically followed it or not. So you have a number of things to think about. I don't want to preempt it, but I want you to think hard in terms of what could be potential sources of error in this kind of an experiment. All right, so I'll stop here. This is just a brief lesson. There is more to the concept of specific heat. I'll give you some discussion questions in the below. You're going to see discussion questions, so you're going to think about the concept of specific heat in general, and also you're going to think about the possible sources of error. So be sure to look at I'll put something below the video so that you can start thinking about the concept of specific heat and the sources of error in general. All right, I'll stop here. If you have any questions, please let me know. Bye for now.